Hello everyone, my name is Anqi from Boston University. I'll be introducing our work, a framework for neural network inference on FPGA-Centric SmartNICs. This work was supported by the PNL DMC LDRD initiative. HPC has been a critical and a growing part of science and engineering for quite some time. An HPC cluster consists of hundreds or thousands of compute servers that are networked together. The nodes in each cluster work in parallel with each other, boosting processing speed to deliver high-performance computing. Machine learning as one of the critical applications aims solving difficult real-world problems using parallel programming models. Performance has been the key reason of putting significant amount of effort deploying high-performance computing with machine learning. There are cluster-based neural network processing such as Microsoft Catapult, Amazon F1 cluster, and the Google Cloud, etc. As problems becoming more complex, compute capacity per device increases, and the burden of communication in HPC network increases as well. The communication takes a significant amount of execution time, which should not be ignored. As the HPC class network evolves, switches, routers, NICs are getting more and more sophisticated. Within the powerful network hardware, network interface card is one of the important components, which act as an endpoint network interface that plugs into the server or storage to enable connectivity to an Ethernet network. Lately, it has been found that if an FPGA can be integrated into the NIC, not only more complex network protocols, but also some data-intensive computation can be efficiently realized when processing network packets without introducing significant overhead. FPGA-based SmartNICs can be viewed as network-focused streaming processing accelerators, in addition to network support devices. This is particularly useful for domain-specific computations, such as in machine learning and streaming data analytics, as the FPGA can be reconfigured as customized accelerators. In this work, we introduce a framework for neural network inference on FPGA-centric SmartNIC, we call it FCSM, that can perform computation, communication, and control altogether at the same time, allowing flexible and fine-grained task creation, distribution, execution across multiple SmartNIC devices. So FCSN is a user-friendly, high-performance FPGA-centric SmartNIC framework, which supports domain-specific computation, low-latency communication, and host-detached scheduling. A hardware-based FPGA-centric SmartNIC runtime that enables asynchronous and fine-grained task scheduling, and a series of streaming neural network kernels that provides acceleration at line rate and maximally overlap computation latency with network communication for neural network applications. FCSN uses data-centric programming model, which provides dynamically sharing hardware resources according to the data locality and brings asynchronous task tokens across cluster of nodes. The asynchronous tasking, which brings computation to data, is achieved by circulating the task token among the cluster, working with its desired data. The token describes the data flow graphs to be executed for a task. This model can provide better parallel scalability with reduced data movement and also supports the concurrent execution of multiple applications, offering ideal architecture support for future high-performance parallel computing and data analytics systems. Here is a list of software API that connects the host applications with its underlying hardware. The FPGA design, which consists of three components. Firstly, Network function handles the communication and the network protocols with the other boards in the system. Secondly, the hardware runtime handles the data-centric program model, the application control logic, and hardware scheduling. Thirdly, the compute engine offers kernel functions which is capable of executing in a streaming manner at network line rate. The hardware runtime handles computation tasks which are traversing the system working with its desired data. When current node does not have the data it needs, it will be re-injected into the network. If the token handler finds out the current node has the demanding data, tasks can be splitted, re-injected into the system, or consumed locally. If task execution requires remote data, RDMA can fetch the corresponding data chunk for the data as needed. When we have received the remote data, runtime handler will acknowledge the task and performs the kernel functions. In FCSM, non-conflict streaming kernel execution at network line rate leverages the SmartNIC capabilities. We provide kernel functions for neural network applications, including 2D convolution, matrix multiplication, function norms, nonlinear element-wise activation, and aggregation. Software-hardware co-design of conflict-free kernel functions on the FPGA-based SmartNIC guarantees that the kernel execution is not stalled and can be tightly combined with the network pipeline. We evaluate the FCSM framework with neural network kernel functions and neural network applications using an Alveo U280 cluster, comparing with CPU and GPU. The results shows that the FCSM achieves an average 10 times speedup over the baseline. For more details, please refer to our paper. Thank you so much for listening to the presentation.